Alright, let's find some partial derivatives. So basically what we're going to be using throughout this problem are, let's see, we have the chain rule, and then we've got these two rules that I've written up here about how you take derivatives. So if x is a variable and a is just some number, then we have just what you learned from calculus, how you take the derivative of x to the a, and then also how you take the derivative of a to the x. Here when I write log a, I mean the natural log of a. So, like, you might write that as ln. But basically, when you sort of get to this level in math, you don't really use different bases of log anymore. Like, there's never really ever a reason to use it. Typically, like, the base of log that you're using isn't really important at all. So, everyone just uses natural log all the time. So, people just write log because it actually is more of an abbreviation for log than ln is an abbreviation of natural log. So whenever I write log, I mean natural log. There's a little thing that I think you do have to be careful about a bit here, because technically, like, you do need there's some stuff that I'm brushing under the rug here, like when we take the derivative of a to the x and we get a to the x times log of a. Of course, this implies that a needs to be a number which is strictly greater than 0, otherwise this doesn't work. And so when we're taking actual partial derivatives in these problems, we're sort of assuming that we're restricting the domain of these functions. Like if you have f of x, y, z is x to the y, then when you take the derivative, there's only certain regions of, like, you can't, the partial derivatives do not necessarily exist for all points in R3. But the details of where they all are defined nicely and everything, like, you can worry about that, but I don't really. This is more the type of thing, like, especially when you're using these types of rules, like differentiation with respect to exponentiation. It's more of like a calculus exercise in which you're just sort of pushing the symbols around, and it feels a little bit more like a puzzle than like an actual, like, thinking about what's really going on underneath. And of course, like, that's the type of thing that you need to be really good at thinking about, and the more you move forward in math, the more important that becomes. But for an exercise like this is just sort of very straightforward computations. Also, sorry that some of these things are a little blurry. That's just how it's written in this particular PDF copy that I have. So I'll make sure to clarify everything that might be unclear. But anyway, so let's start with f of x, y, z equals x to the power of y. So let's see here, we want the partial derivatives, so derivatives with respect to x, y, and z. So d1 f of x, y, z. So 1 means the first coordinate, so we're taking the partial derivative with respect to x. So y is a constant, which means that taking the derivative, it's like the first scenario I have up here, where you just bring down the exponent and subtract it by 1. So we're going to end up with y times x to the power of y minus 1. This example is actually already given in the chapter if you read through it. So we've got d1 of f equals this, and then d2 of f. Just to condense my notation, I'm not going to write the x, y, z in parentheses here, because, like, you can sort of assume that needs to be there, so you can just not write it and just sort of understand that that's there. Just pretend that I've taken the extra time to write it out. Anyways, so again, using our rules here, d2f, y is the variable, so we get x to the y times log of x. And then, what if we take the derivative with respect to z? Well, with respect to z, x to the power of y is just a constant, so the derivative is 0. Alright, so that's easy enough. Even easier, we've got f of x, y, z equals z. So if you take the derivative with respect to... So there's no x or y in this formula. So taking the derivative with respect to x or with respect to y will give you 0. And if you take the derivative with respect to z, then you'll end up with... you take the derivative of z and you just get 1. That's just the power rule. So yeah, for this reason, like, you have to sort of keep in mind that x, y, and z are 1, 2, and 3, and it's really not that difficult, but I sort of like how, like, sometimes you'll have like, if you write it as, like, u, x, y, z equals z, then sometimes, like, especially when you're dealing with, like, differential equations, a common notation is you take u and you use a subscript to denote which coordinate you're taking the derivative with respect to. So the derivative of u with respect to x equals the derivative of u with respect to y, which equals 0, and the derivative of u with respect to z equals 1. So that's just an alternative notation that you might find useful. I sort of prefer it, but just to keep consistent with the exercise here, I'm not going to use that. Okay, so this one, and of course I'm going to continue to start these by writing out what it is, so that, because I'm going to scroll down a lot. So sine of x times sine of y. Okay, so if we want to take d1 of f, that means we need to take the derivative of this thing with respect to x. So the first thing we do is we sort of see that this is a function within a function. You've got sine, and then sine is a function where you plug in something into here, and what we have on the inside here is an additional function. So when we take the derivative, we have to take the derivative of cosine and just leave all this, or we have to take the derivative of sine and leave all the stuff in the middle there. So the derivative of sine is cosine, so we take cosine, and then we leave the x sine y that's on the inside, we leave that alone. But then what we have to do is we have to multiply this by the derivative with respect to x of all the stuff that was on the inside. So x sine y. So this is going to give us cosine of x sine y. And then if we take x sine y and take the derivative with respect to x, well, sine y is just a constant, and take the derivative of x, you get 1, so you'll end up just multiplying by sine of y. d2 of f equals, oh, this is only a function of x and y. Okay, so there's no z. Well, if it were a function of x, y, and z, then the derivative with respect to z would just be 0. Anyways, so d2 of f, we get cosine of x sine y. We multiply by d2 of x sine y. This is just the chain rule again, but here we have d2 instead of d1. And so this will become cosine x sine y. And now when we take the derivative of x sine y with respect to y, x is just a constant. And when we take the derivative of sine of y, we'll get cosine of y. So there we go. Alright. Oh man, we go all the way to I. Okay, well, and these start to get harder. So, f of x, y, z equals, oh boy, sine of x times sine of y times sine of z. So this is just more chain rule. So d1f is going to be, so we start at the very outside. We've got this sine here on the outside, so that's going to become cosine, and we have to leave all the stuff on the inside. Y sine z. And now we have to multiply by the derivative with respect to x of all the stuff that was on the inside, which is x times sine of y sine of z. Okay, so we have that. And now when we evaluate this derivative here, we again need to use the chain rule. So this cosine x sine y sine z, that's there again. And then when we take the derivative of this, okay, well, we've got the sine of y times sine z. There's no x in there, so that's just a constant. So when we take the derivative with respect to x, we just get sine of y times sine of z. Okay, so that's not too bad. Let's keep going here. d2 of f. So the first part is going to be, nope, that's not the button that I wanted to press. I want to copy and paste this. But it looks like that's going to take longer to do than just writing it out. So I'm going to write it out. Starts out the same, but now we have d2 of x times sine of y sine of z. So now the y here is on the inside, and so in order to sort of extract that, we need to do the chain rule again. Oh, wait, no. Yeah, we're good. Okay, so when we take the derivative, the x stays there, and then we have to do the chain rule, so the sine of whatever becomes cosine of whatever. Then we have to multiply by d2 of the stuff that was on the inside, which is y sine of z. So finally, we get all of the stuff that we had before, which I am just going to completely rewrite. X cosine y sine of z times, and then when we take the derivative of this with respect to y, we just end up with sine of z. So you see, every time we take a derivative, we basically have to use the chain rule multiple times until we get to whatever variable we're at. So first time, for the first variable, we had to do chain rule once. Second variable, we had to do it twice, and you should be able to see a pattern. For the third variable, we're going to have to use the chain rule 3 times. So here. So we'll multiply by d3 of x sine y sine of z. Oh wait, will we need another one? Let's see. Cosine x sine y sine z. Then when we take the derivative of this, x is again just a constant, and we end up with cosine of y sine z. Oh, I guess we don't need to use the chain rule again here. We only need to use it 2 times. Because here, we're just taking the derivative of y times sine of z, and of course, sine of z is going to become cosine of z, and the y is going to stay there because it is a constant when you're taking the derivative with respect to z. Alright, and that finishes part D. Now we move on to part E, and we have f of x, y, z is equal to x to the power of y to the power of z. So d1f equals, well, x is being raised to the power of y to the z, so let's write that. So d1, we write this as x to the power of y to the z, because y to the z here is just a constant. And so we use that rule where we bring down the exponent, multiply by x, and then raise to the power of whatever exponent we had, minus 1. And that's all we have to do there. And there's no x's in that exponent, so we don't need to worry about the chain rule or anything. How about d2 of f? So we've got x to the power of y to the power of z. So we have x, when we take the derivative, well, we've got x raised to a function of y. So we do need to use the chain rule here. So x raised to a function of y, so we're going to start with pretending that that function of y is just a thing. So we take x to the y to the z log of x, because that's what we would do if it was just x raised to the power of y. But here it's x raised to the power of a function of y, so you do sort of the outside of the function. But then you multiply by the derivative of that function of y that we were using. So this is a derivative with respect to y of the exponent. And so let's see here, the x to the y to the z log x part stays the same. And here we multiply by the derivative with respect to y of y to the z, which this is, again, the same rule that we used in the previous example, where you bring down the exponent and you subtract by 1. Then finally we have d3 of f, and I'm going to write this as d3 of x to the power of y to the power of z. And so you think of the x to the y as just a constant here. And so what this is going to become is, we can, wait, is this correct? Right, yeah, it's going to be x to the power of y to the power of z times the log of x to the power of y. Is that what I have before? I don't know. Let me think about this. x is being raised to the power of y, which is being... Oh, no, this is wrong. Because x to the power of y raised to the power of z would be x to the power of y times z. That's not what we're doing here. Oh, and now that I see this, I'm actually concerned that the first part that I did was wrong. So let's think about this. So we have x to the y to the power of z. Then that would be y to the z times that. No, the first part I think is okay. This part I don't think we're able to do this here. So it's x to the y to the z. Right, because it's x being raised to the power of y to the z, and y to the z is a number there, so that's fine. Here, x to the y being raised to the power of z is not the same as x to the power of... Yeah. So what we have to do here is y to the z is a function of z, so we do the same thing that we did in the previous example, so this is x to the y to the z times log of x. That should just be log of x times d3 of y to the z, and so this is going to be like the previous example, but the final step is going to be different. So instead of z minus 1, we're going to end up with y to the z times natural log of y. So there we go. So that's that. Now we move on to the next part of the problem. Hooray. So f, which we have f of x, y, z is equal to x to the power of y plus z. d1f is going to be, well, it's just x raised to some power, and so we bring down the exponent and then subtract 1. d2f is going to be, well, here we have to do the thing where we do, so it's x raised to the power of a function of y, so we treat that function of y, so we first do the outside part, then we multiply by the derivative with respect to y of the exponent. And when you take the derivative with respect to y of y plus z, the y will become a 1 and the z will become a 0, and so this is just going to be x to the y plus z times log of x. And, okay, so the derivative with respect to y of y plus z is 1. Similarly, it turns out that d3 here, I'll actually write this out. So this is, it's going to start out the same, and, well, when you take the derivative with respect to z of y plus z, you also get 1. So it's not only is it going to start out the same, but it's going to end the same. So log of x, and there you go. That's f. Man, we still have 3 more of these? Couldn't you have, like, made these, like, all different exercises so that you feel more... When you do all these exercises, you feel like you've done more work than just having all of these as part of one exercise you finish and you're like, oh, I've only done one exercise. Whereas it really feels like you've done like 20. Okay, maybe that's a slight exaggeration, but so here we got x plus y being raised to the power of z. So d1f is, let's see here, so taking the derivative with respect to x, so the z comes down, x plus y, z minus 1. Then we have to multiply by d1 of x plus y. And of course that's again going to be 1. So z x plus y to the power of z minus 1 is our final answer. And it turns out you're going to get the same thing for d2 of f, so I'll just write that here because it's the same exact computation. It's just like in the previous example. D3 is where it gets a little different. We have to keep what we have before and multiply by the natural log of what's on the inside, or what's natural log of the base, and yeah, that's it. Okay, so that's all right. Oh, I think this next one isn't too bad either. H, we've got f of xy equals sine of xy. D1f. Well, when you take, this is just the chain rule. When you take the derivative of sine, you get cosine. So we start with cosine of xy times the derivative of xy. And the derivative with respect to x of x times y, well, x will become 1 and y is a constant, so it stays there. So this is going to be y cosine of xy. And then d2 of f is going to be cosine of xy, d2 xy, and so that's going to become x times cosine of xy. Okay. And then finally we have I. So what is I going to be? We've got f of x, y, z equals, and I'm going to write this like this. So we have sine of x times y to the power of alpha, where alpha equals cosine of 3. So cosine of 3 is just some number. It's not 1 and it's not 0, so it doesn't cause any strange things to happen. But it's just a number, and instead of having to write out cosine 3 every single time, I'm just going to write alpha. Okay, so... Oh, this is not with respect to z. This is just x and y. Okay, so d1 of f equals... So we bring down the exponent, multiply by sine of xy, raised to the power of alpha minus 1. And then we have to multiply by d1 of sine of xy. Oh, but we did that in the previous exercise, so this is not too bad. So this is going to be alpha of sine xy to the power of alpha minus 1. Then what's the derivative with respect to x of sine of xy? Let's see, we ended up with y cosine of xy. So y cosine of xy. And then d2 of f, we're going to solve similarly. So this is going to be alpha sine xy to the alpha minus 1 times d2 of sine of xy, and we know what that is already. It's we already know what that is. We know that's x cosine of xy, and so that's that. And now we are done with this exercise.